Hello and welcome to our very last lesson of functions and applications, where today we are looking at word problems involving sine function. So with these word problems, we are often given a function and we're asked to evaluate or interpret the function based on the parameters that we saw previously, so A, D, and C. And previously, the problems we saw, we had the independent variable as degrees, and we had that the domain could be the set of all real numbers. And for example, all the positive x values were uh, motion in one direction, whereas uh, in the negative x values, it was movement in the opposite direction. So for example, clockwise versus counterclockwise. And now, with some of these word problems, we're going to see that the input of our sine function may be different. So the independent variable could perhaps be time. And as well for word problems, we have restrictions based on the context of the problem. So we do have to account for that in our domain and range. So let's get started on our first example. So we have Emma is designing a clock-themed display for a museum, and she wants to model the vertical position of the tip of the minute hand throughout one complete rotation. The minute hand is 12 centimeters long and rotates around the center of the clock. At 12 o'clock, the tip of the minute hand is at its highest point, and the function, which is h of t, is equal to 12 centimeters. And this is all what's given to us in the problem itself. Now, let t represent the time in minutes after 12 o'clock, and t is going to be between 0 and 60 minutes inclusive. And consider 1 hour, which is 60 minutes. And h of t represents the vertical position of the tip of the minute hand above the center of the clock in centimeters. And we're already told the equation, which is h of t is equal to 12 sine of 6t plus 90 degrees. And we have that 6 there, if you remember from last class. This has to do with our horizontal stretch and compression. So here we actually have a horizontal compression because we have k as equal to 6, which is greater than 0. So that means one period is going to be 60 minutes. So connecting that to the 360 degrees, we are completing a 360 rotation, but over 60 minutes because our independent variable is time, so the 60 minutes there, which means we have a 6-degree rotation per minute. Now we're asked first to identify the independent and dependent variable and any restrictions on each variable. So of course the independent variable here is t, which is the time in minutes, and it is precisely the time after 12 o'clock. And we have t between 0 and 60 inclusive because we are only looking at one rotation over 1 hour. And yes, it's true that the minute hand can keep rotating past the 60 minutes, but we only want this cycle. So we are restricting our domain, given the context of our problem, for 1 hour only. And the dependent variable is the vertical position of the tip of the minute hand, and it is our function h of t, and this is in centimeters. And for this as well, and I will add this in for you after, but we do actually have a restriction on this as well because h of t is going to be between negative 12 and 12 centimeters inclusive. The reason for that is the height of the minute hand is 12 centimeters, which means that from the center, when it's directly above, then this is 12 centimeters, and when it is directly below, that's negative 12 centimeters. So we can't go past that height, so we actually do have a restriction there as well. Next, we're asked to state the amplitude, period, and equation of the axis and interpret these values in the context of the question. And again, for the sake of this, because I'm working through this problem with you, I included the horizontal stretch and compression there, but we are going to still just use what we know about the problem to answer this. So of course the amplitude is 12 centimeters, which we get from the coefficient A, and this tells us the tip of the minute hand moves a maximum of 12 centimeters above and 12 centimeters below the center of the clock, which is what we had over here. Now the period, and really we don't need to know the the horizontal stretch and compression here because we know that the period is 60 minutes because we are considering one full rotation over 1 hour. Now, the equation of the axis, which is h of t is equal to 0, represents the center of the clock as the midpoint for us. So when we are considering the motion, then the center of the clock is going to be the center. So again, when we go the maximum or minimum, it is with respect to that center of the clock. And exactly here, the tip of the minute hand is oscillating equally above and below this height, which makes that our equation of axis or the midline. Now we're asked to determine the height of the tip after 15 minutes. So this is just when t is equal to 15. So we substitute this value into our equation. So h of 15 is 12 times sine of 6 times 15 plus 90 degrees, or 90. And this is equal to 12 sine of 180 degrees, which is equal to 0 centimeters here, which means after 50 minutes, the tip of the minute hand is level with the center of the clock. And that actually makes sense because if we are starting at 12 o'clock, which means that our minute hand is at 12, then after 15 minutes, our minute hand is now here, which means it is in line with the center of the clock. And so the height is 0. Next, we're asked at what time or times is the tip exactly 6 centimeters above the center of the clock? And of course, as we know with the clock, this can, and this should be your hint here as well because it says times, we can have a height of 6 centimeters this way or this way. So there will actually be two different times in which we have a height of exactly 6 centimeters above the center of the clock. So we are solving for h of t is equal to 6 in this case. So that means 6 is equal to 12 sine of 60 plus 90, or sine of 60 plus 90. And here I just divided 6 by the 12 to get half. Now, this is just a sine of something is equal to half. So first, I'm just going to use what I know about the key points of the sine function. So we know that sine of 30 degrees is equal to half, or if you weren't sure, you can do the sine inverse of half to get 30 degrees. But we are actually solving for sine of where our input is 6 times t plus 90 degrees. And because we have 90 degrees, and remember, our t was restricted to be between 0 and 60 degrees, or 60 minutes inclusive, then there's actually no value of t where this will be equal to 30 because we're already starting at 90 degrees. And even if this is equal to 0, which is the minimum value of t, then this will not be equal to 30. So we have to consider now the property of this being a periodic function. So we look for the next possible values where sine of x is going to be equal to 0.5. So again, we're only looking first at our parent function for sine. So approximately here is 30 degrees where we have sine of x is equal to half. So then another time this happens is over here, which is 180 minus 30, or that 150 degrees. And another point again is over here, which now this is one full cycle, so it's 360 degrees plus 30 degrees. And this is 390 degrees, and you can double check that the sine of both of these inputs gives us 0.5. But again, we had sine of 6 times t plus 90 degrees, and so really we want to find for what value of t is this input equal to 150 degrees and then 390 degrees. So first starting with the 150 degrees, we find that t is equal to t. And for the 390 degrees, we find that t is equal to 50, which means that the tip of the minute hand reaches a height of 6 centimeters above the center twice during each rotation during 1 hour, once at 10 minutes when it's moving downwards, and once at 50 minutes when it's moving upward. And let me just replicate this here for us. Oops. And again, that makes sense from our graph. So after 10 minutes, we are approximately maybe here. And then at 50 minutes, we are approximately here. And this could be 6 centimeters above this midline here for us. Now, the next question for you to think about is how would this solution change if you were asked to solve for the times when the tip is exactly 6 centimeter below the center of the clock? So what you would have to do here, instead of h of t is equal to 6, as we had written here, you would just have h of t is equal to -6 now because we are going below the midline. And again, you would just have to use the same process to find which values of sine of x produce -½ because you would still have the um, you would just have the negative now. The actual value of half would not change. And so then you can use this a similar process to this to find those two different times. Now for our next example, Marcus and Ava are visiting Skyview Amusement Park and they decide to ride a new Ferris wheel called the Sky Flyer. The Ferris wheel has a radius of 18 meters and the center is 20 meters above the ground. The ride begins with Marcus seated at the lowest point of the Ferris wheel, so at the minimum point, and the ride completes one full revolution every 180 seconds. So that's our period there. So again, we have our independent and dependent variable defined here for us. So let t represent the time in seconds since the ride began. And again, we're only looking at one full revolution, which is why t is restricted to be between 0 and 180 seconds. And h of t represents Marcus's height above the ground in meters. Now, again, here we have the equation given to us where Marcus's height is modeled by 18 times sine of 2t minus 90 degrees plus 20. So just interpreting this, 18, of course, is my amplitude or the radius of the Ferris wheel. This 2 is my horizontal compression because instead of 360, we are completing the cycle in 180. So we have divided our period by 2. And then we have this shift to the right by 90 degrees. And the reason for this is because we aren't getting on the Ferris wheel at the midline, which is what happens with the parent function for sine of x. So we are actually getting on at the lowest point, which is at the minimum. And so knowing that my sine function is as such and this way, remember that this point here, which is the lowest point, is negative 270 and -1. So if I shift everything by 90 degrees to the right, that means that my resulting graph will be, or maybe let me draw it with the red, will be here, and then I will have something like that. So I'm getting on, or Marcus is getting on at the lowest point at time 0. And finally, the plus 20 is the midline or the center of the Ferris wheel above the ground, which was 20 meters above the ground. And from here, we also note that the Ferris wheel rotates at a rate of 2 degrees per second, and that makes sense for one full cycle to take 180 seconds. So a 360 rotation is completed over 180 seconds. So again, our dependent and independent variable here, we're just repeating it. And so we do have that The independent variable here is time in seconds, and it is since the ride began. So t is between 0 and 180 seconds inclusive. And the dependent variable, which is h of t, which is Marcus's height after t seconds. Oh, and it's actually in meters, sorry. It's both in meters, and again, I also forgot for this one to mention the restrictions, but we do have that h of t is actually going to be between 2 and 38 inclusive. And the reason for this is from the midline 20, I have a radius of 18, so then my minimum point is going to be 20 minus 18, which is 2, and my maximum point is going to be 20 plus 18, so 38 meters. Now state the amplitude, period, and equation of the axis and interpret the results. So the amplitude here is 18 meters. Again, this is the radius of the Ferris wheel, and we note that the rider, in this case Marcus, moves 18 meters above and then 18 meters below the center of the Ferris wheel during each revolution. The period is 180 seconds, and that's how long it takes for one full revolution. And so the cycle is repeating every 180 seconds. The equation of the axis h of t is equal to 20, and this represents the center of the Ferris wheel, or how far off the ground the axle of the Ferris wheel is, which is 20 meters. And so Marcus's height is oscillating about this, the axle, which is, again, 20 meters above the ground. Now, determine Marcus's height after 50 seconds. So here we have t is equal to 50, so we're just substituting this value in. So actually this is h of 50, and this is equal to 18 times sine of 2 times 50 minus 90 and plus 20, which is approximately 23.1 meters. So after 50 seconds, Marcus is approximately 23.1 meters above the ground. And we're now asked, at what other time is Marcus the same height as when t is equal to 50 seconds? So here we already had, we can pretty much use the information that we were evaluating here. So we know that 18 times sine of 10 degrees, which is the input here, plus 20 is approximately 23.1. We want to find another value, not of x, of t, or actually sorry, it is x because we're looking at sine of x, the parent function, and then we we substitute that value in to find our t. So we want to find another value of x such that sine of x is equal to sine of 10 degrees. So considering the graph of sine of x, again, consider this graph here. So one option here is at 10, but knowing that this is symmetrical about 90, then the other point is here, and knowing that this is 180, this is just 180 minus 10, or 170 degrees. And we can now double check. 18 times sine of 170 degrees plus 20 is approximately 23.1 as required. And now we can substitute for that 2t minus 90 degrees, which is the input of our function, and we want this to equal 170, so that t is equal to 130 seconds. So Marcus reaches a height of approximately 23.1 meters twice during one revolution, once while he's ascending, going up, so at 50 seconds, and another time while he's descending at 130 seconds. Another type of question you might be asked is, during what time interval is Marcus above 30 meters? So to do this, you have to find the times at which he is at 30 meters, and then the time in between those points is the time where he's going to be above 30 meters. So really, we want to solve for h of t is equal to 30. So here we rearrange, so we have a subtraction of 20. So 18 times sine of 2t minus 90 is going to be equal to 10. And again, we divide by that coefficient to get 10 over 18. So what values of sine are going to give me 10 over 18. So here I'm just taking the inverse ratio of sine, so I get 33.7 degrees. Now, similar to above, we want to check for what other value is this ratio going to be equal to 10 over 18. And again, as above, we have 180 degrees minus 34 degrees. So I just rounded this up. With angles, you can always round up to the nearest, round up or down to the nearest degree. So then the other degree is 146 degrees. And now we solve for both of the t values that correspond with these two angles. So t1 from 34, and I'm just substituting this for 2t minus 90 to find what t is. This gives me 62 seconds. And the second time for the 146 degrees there is going to give me 118 seconds. So at times t is equal to 62 seconds and t is equal to 118 seconds, Marcus is at 30 meters. So during the time interval between that, so when t is between 62 and 118 seconds, not inclusive of those times, Marcus is above 30 meters. And it is not inclusive of those times because we're asked for the height above 30 meters. Whereas if you were asked at what time is he 30 meters or higher, then you can consider the range to be inclusive of those times as well. And now we have our very last example where here we actually have to come up with the equation that models the situation ourselves. So we are told that skyscrapers sway in high wind conditions. In one case, at t equals 2 seconds, the top floor of a building swayed 30 centimeters to the left, and we're told that this is negative 30 centimeters. And at t is equal to 12 seconds, the top floor swayed 30 centimeters to the right, so this is plus 30 centimeters of its starting position. We're asked what the equation of a sine function that describes the motion of the building in terms of time is. Now, this is not a circular motion. This is actually an oscillating motion where if this is our building, it sways right and left, right and left. So here we have t is the time in seconds, and y of t is going to represent the motion of the building as a function of time. So again, we are going to first start by just analyzing the characteristics or the properties that are required for the function. At its starting position, we know that it hasn't swayed. So when it's swaying left and right, that is actually our amplitude of 30 centimeters. And especially because it is negative 30 and plus 30, which is what we require for our amplitude, given that the equation of the axis in this case is y is equal to 0, and that's exactly what we have. At in its starting point, we would expect that the building is just, it's not swaying. So we have that the movement is y equals to 0, so that when it moves right and left, it goes to plus 30 and negative 30 centimeters. Now, at time is equal to 2, we have the minimum displacement of negative 30 centimeters. And at t is equal to 12 seconds, we have the maximum displacement, so plus 30 centimeters. And again, this is about the equation of the axis of y is equal to 0. Now, we can also find the period. So the building moves from its minimum position to its maximum position, which is from 12 to 2, from between 2 seconds and 12 seconds, which is 10 seconds. Now, from the minimum to the maximum position, that's only half of the cycle. We always want to consider from one trough to another trough or from one peak to another peak. So then we say that the period is double this, which is 20 seconds. And we actually have a horizontal compression here because our period is not 360. So we have to find what that scale factor is by dividing 360 by the period here, which is 20, and we get that it is 18. Now, we also find that the graph will cross the midline or the equation of the axis when it's increasing halfway between the minimum and the maximum. And this happens at the average of those two times, so the 2 second and the 12 seconds, so at 7 seconds. Which means that knowing our graph of our sine function, which is something like this being the positive cycle is going to be at time is equal to 7, which means that we are first shifting our complete graph by 7 seconds to the right for this to go upwards at 12 seconds and then go back down. And also from the opposite way, if we shift from this minimum 7 over, then that's going to be the minimum at time is equal to 2 seconds. Now, we also have to follow order of operation here when it comes to having both horizontal stretch and compression as well as horizontal translation. So we have to do our shift first, and then once we have the placement, then we can actually stretch out or compress the graph, which in this case we are compressing. And that's why we have our equation set up like this. So because the equation of the axis or the midline was 0, we don't have any vertical translation, so nothing here. But our input has a translation and a compression. So again, following order of operations, I have to shift 7 units to the right, so 7 seconds right first, so t minus 7, and then I'm going to multiply this by 18 for this to be my compression by a scale factor of 18, such that the period will be 20 seconds long. And of course, this 30 is my amplitude or the range of motion as the building is oscillating about its starting point. And looking at the graph here, I just graphed that function there. This is exactly what we see. At time 2 seconds, we are at negative 30. At time 12 seconds, we are at 30. One full cycle is between 2 to 22, so that's 20 seconds there. Or from here, from 12 to 32, that's another 20 seconds. And of course, this amplitude here is 30, which is the range from the starting position to the right, and then 30 here, which is to the left. And of course, we can see this is a compressed graph compared to our regular parent function for sine of x. And yes, it has been shifted to the right by 7. And we can see that at this point, which is t is equal to 7 is when we are starting our positive cycle, which means that we are going up and down, and that's why we have that shift to the right. And yes, that was the completed equation that models this situation. And that was the final example for our lesson and also our very last lesson for the course. So I hope you learned lots and you were able to challenge yourself throughout this function. And thank you all for joining for all the lessons. And I wish you the best of luck in your future courses. And I hope you continue to learn and have lots of fun with mathematics.